Let's work out a few examples of using this idea of finding the radius of convergence and therefore the interval convergence of a power series. Here's a power series. The sum from n equals 1 to infinity of x minus 3 to the n divided by n. We'll use the ratio test to find the radius of convergence, and then with that we'll determine the interval of convergence. So, according to the ratio test, this series converges when this limit is less than 1 of a to the n plus 1. So I'm going to replace every n with an n plus 1. I'm going to end up getting a fairly gigantic fraction, at least gigantic by our standards. X minus 3 to the n plus 1 over n plus 1. And then we'll have an x minus 3 to the n over n. So the absolute value of the ratio of these two fractions, this is, let's simplify this a little bit, flip the second guy and multiply, and let's stack some terms that are alike. I think there's an x minus 3 to the n plus 1 on top, and also an x minus 3 to the n over here, so I'm going to have a single fraction of x minus 3 to the n plus 1 over x minus 3 to the n. There's an n plus 1 on the bottom of this fraction in the numerator. There's an n on the bottom of the fraction denominator. When I flip this fraction, this n will now be in the numerator. So let's simplify. X minus 3 to the n plus 1 divided by x minus 3 to the n is just, well, x minus 3 with no n's, which means the limit doesn't really affect it. X minus 3. And we're left with the terms that does have n's, n over n plus 1. The limit of n over n plus 1 as n tends to infinity is 1. Meaning you could, according to our previous definition, we would say that L is equal to 1. We know this converges when x minus 3 times 1 is smaller than 1, or when x minus 3 is less than 1. This tells me, well, I've gotten the absolute value of x by itself. This tells me that the radius of convergence is 1. We're going to use this now to determine the interval of convergence. That interval of convergence is the solution to the absolute value inequality, x minus 3 is less than 1, or negative 1 is less than x minus 3, which is less than 1. Or 2 is less than x is less than 4. Inside of this interval, this series definitely converges. What we don't know, because the ratio test is inconclusive when the absolute value is equal to 1, so we don't know what happens at exactly these endpoints. What that means for us, for our solution, is that we don't know whether these are or equal to's or not. We need to determine that, and we can. We can determine that by substituting in these values of x into the original series, and using one of our infinite series convergence tests to decide what that looks like. So we need to decide look at these two cases, when x is at either endpoint. How about when x is 2? When x is 2, this series becomes 2 minus 3 to the n over n, which is the series from n equals 1 to infinity of 2 minus 3, which is negative 1 to the n over n. This series converges by the absolute value, by the alternating series test. this converges by the alternating series test. When x is the other endpoint, we get this series of 4 minus 3 this time. And 4 minus 3 is 1. This is 1 to the n, or 1 over n. And this series diverges because it's harmonic. Put these together, what does this say? This says that since this converges when x equals 2, that means that in my interval, x could be definitely 2 because it converges at 2. It does not converge at 4. So in the end, I know that the interval of convergence is 2 is less than or equal to x is less than 4. Or in our interval notation, how about close bracket to open bracket 4. Okay, let's try this again, just as another example. How about this more complicated looking series? How about sum from n equals 0 to infinity of minus 3 to the n times x to the n over root n plus 1. So same directions. Let's again try to find the radius of convergence, and then we'll use that to find the interval of convergence. So again, according to the ratio test, we need to find the limit as n tends to infinity of, replace all the n's with n plus 1s. N plus 1 plus 1. Then we divide this by, well, the expression which is n's. X to the n over square root of n plus 1. Okay, just as before, I'm going to try to simplify this. Again, I'm going to flip the second guy and multiply. Of, let's see, what was on top here will stay on top. What was on top in the denominator will be on bottom now, and vice versa. What was the denominator of the top will be still the denominator. The denominator of the bottom will be the new numerator. Will be in the new numerator. So if I kind of match things up here, I have a minus 3 n plus 1 on the numerator and a minus 3 to the n in the denominator. I have an x to the n plus 1 on top and an x to the n on bottom. And I also have a root n plus 1 or root n plus 2 in the denominator and a root n plus 1 in the numerator. Can do some simplifying. The ratio of this guy here is just minus 3. The ratio of x to the n plus 1 over x to the n is just x. And this is, well, it's root n plus 1 over root n plus 2. These two terms do not depend on n, so I can pull them out of this limit. This would be the absolute value of minus 3, which is just 3, absolute values of x, and then my limit. This limit, you could do, if you're not quite sure what this limit evaluates to be, you could make this one big square root n plus 1 over n plus 2. You could divide each individual term by n, and you'd find pretty quickly that this limit tends to 1. So what's this say? This says that this limit, that this expression, this ratio test tells me, leaves me with this expression, 3 times the absolute value of x. And the ratio test tells me this converges when this is less than 1. Or I could get the absolute value of x by itself, divide by 3, and I find that the absolute value of x is less than 1/3. So the radius at convergence, therefore 1/3, how about 1/3 is the radius of convergence. So from this tells me that the interval of convergence is at least the solution to this. The absolute value of x is less than 1/3. That tells me that negative 1/3 is less than x, which is less than positive 1/3. Just as before, this is when x is guaranteed to converge, the function is guaranteed to converge. We need to test, will it converge at either of the endpoints? So again, as we did before, I'm going to substitute in each of the endpoints into my original series and use one of my infinite series convergence tests to decide if it converges at for that x value. When x is 1/3, this gives me the following series, n from 0 to infinity of -3 to the n times 1/3 to the n over root n plus 1. These terms have the same exponent, so I could combine them into one term. This would be like -3 times 1/3 to the n, which is -3 times 1/3 is -1. And when you know this is an alternating series, and this converges by the alternating series test. So when x is 1/3, life is good. Similarly, when x is -1/3, -1/3 to the n over root n plus 1. -3 times -1/3 is 1. This is a p series. This is a p series with p is equal to 1/2. P series only converge when p is strictly greater than 1. So this diverges. Put these things together. The interval of convergence, therefore, is this converges for -1/3 x less than or equal to positive 1/3. Does not converge at -1/3, but does converge at positive 1/3.